Okay, well, thanks a lot, Tomasz, Kania, for coming here to our seminar, especially for coming this horrible time. And yeah, please, you can start the talk.
Okay, thank you very much. It's really a pleasure to me. The last time I was in Virginia and gave a talk at your seminar was something like 5 years ago, and then I remember David's hospitality and also Kevin's. It was a really great time. So I'm very happy actually to talk once again here in Virginia. So the talk I'm going to present is based on a single paper with a postdoc of mine from Prague. The paper is actually quite unusual, and I'll try to sell you the whole story. So the talk is going to be an advertisement for a certain method rather than the presentation of the main result. The main result will come as an illustration to a certain set theoretic magic that I'll try to convince you to. Okay, so the general structure of the talk is to give you some background on actually motivations from set theory. I'm not going to talk in details about the main tool, which are the so-called super compact cardinals. I'll try to explain what they do instead of what they are. And here it is. So let me start from the very beginning. And when I say from the very beginning, I do mean it, because let me start from the empty set. Yes, so it is like giving a talk about, I don't know, history of I don't know, the Second World War, talking about dinosaurs. This is this scale, but this actually fits nicely into the picture. So let us construct the universe of all sets. So everything can be constructed from the empty set. So how we do it? Well, we take the empty set, we take the power set of the empty set, which is not maybe the most exciting object to look at, but we proceed transfinitely with overall ordinals. So when we are at the, let's say, successor step, we'll simply take the power set of the structure that was previously constructed. Yes, so actually V1, V2, V3 are quite trivial objects, although of increasing cardinality. And at limit steps, we simply take the union of the objects we have created. So in that way, we can, well, what we did, if we, let's say, take the union over all ordinals, then we have constructed the class of all sets. Yes, so you can actually prove that every set you're working with, I mean set in the sense of ZFC or ZF, actually appears at some stage of this construction. So it is somewhere here. Okay, so you can think of V as a model of ZF, of the usual set theory, let's say without the axiom of choice for now. Let us forget about the axiom of choice. So it is like a cumulative hierarchy of sets. Yes. So this is actually nice because in V, well, we said that it is like a model of ZFC because it is a model. However, we should take caution that V is a proper class, not a set. And usually, when we talk about models of something, of some theory, we talk about sets. So with that only difference, this is like the model of ZF, and actually we can call it either an inner model or a class model to emphasize that V is not a set. Okay, so we have this hierarchy, but when we, let's say, go to some ordinal, to some limit ordinal, such as the first uncountable ordinal, then this structure behaves is a set. Yes, when you terminate at some limit, or not necessarily, but when you terminate at some limit ordinal, then it is a set. And it is almost a model of ZF, with one exception, possibly, there could be a problem with taking the power sets. So the power set axiom need not be satisfied. But maybe sometimes it will be, depending on the initial on the ordinal that you stop, that you terminate at. But if you can do it, so if you can prove that that for some ordinal you have a model which is a set, well, then you have to face the Goddale theorem, which tells you that you have, since you found a model to a theory, here this theory is ZF, well, it means that this theory is consistent. Yes, but we do know that ZF or ZFC does not prove its consistency. It can't, simply can't. So if you can find an ordinal such that this gives you a set model, well, this has to be done in a theory, in a meta theory that is way stronger than ZFC alone. But we will return to this issue in a moment. But let us put this into perspective. So some people who maybe are not overly fond of set theory will say that, well, yeah, this is maybe an interesting construction, but the normal mathematics takes place in, I don't know, V omega, or at most V omega squared. So not that high, yes. And in, let's say, in most of maths activities, maybe besides set theory, you can't really reach, I don't know, V omega to omega, which is still countable level, or V omega 1. But V of omega 1 or V of any explicit Aleph function, that Aleph cardinal that you can write down, will not satisfy the power set axiom. So if there is an ordinal or cardinal for that, so that we do have a model of set theory, it has to be huge itself. Therefore, this initial part of the cumulative hierarchy will be humongous in comparison to, let's say, the realm in which most of the mathematics takes place. So you could think of this, or you could say that it is kind of esoteric, and hence, why do we bother? So maybe people doing some crazy non-separable stuff will be interested in it, but we normal mathematicians, as people like to think about themselves, say, well, let us leave this to logicians. But we will see that maybe there are actually some applications to it. Let me change the topic slightly, and actually most of you probably will know the answers, but let me tease you anyway. We have the following trivia from let's say measure theory 1. Well, when we have two Borel sets, let us say in the Euclidean spaces, and we take the product, then the product is of course Borel, so it is a measurable set. Okay, so far so good. So let us take a Borel set in the product of two Euclidean spaces, and project, let's say, onto whatever hyperplane you like. Is it Borel? Is it measurable, this projection? Well, no, it need not be Borel, but it will be measurable. It will be still measurable. This is interesting and useful, and I'll explain how we can benefit from this in a moment. But it is so the projection need not be Borel, but it is measurable. Okay, so now let us do the following. So take the complement of the set that you constructed this way by projection. Take the complement and project that complement onto whatever hyperplane you like. Could be one-dimensional, could be or could be like a line, could be a two-dimensional plane, hyperplane, whatever. Is this object, is this set measurable, or does it have the Burr property? So can you write it as a symmetric union of an open set and meager set. Well, it should be measurable, yes, that's our expectation, because what we did, we took a set, we took a complement, so this is very much measure theoretic operation, and we used a very decent map, the projection onto hyperplane. But what about measurability? Okay, so probably those who know, maybe we shouldn't spoil it now, but this is something that appeared in a paper by Lebesgue, where he was, I think it was the paper that introduced the Lebesgue measure, and he said, of course, this set is measurable, yes, and such statements should always raise the red flags. And Luzin was studying that paper and was desperately trying to fix it without, let's say, any success. And he couldn't. Yes, he couldn't, because you cannot really decide this. You can't really decide this in ZFC alone, but the nature of this is different, let's say, from the continuum hypothesis or Martin's axiom. I will arrive at this. So this is not exactly that reason for which, let's say, you have a problem with the continuum hypothesis. Okay, so let's say that for now, maybe we don't know whether it is measurable or not, but we can define a hierarchy of sets of this kind. So let us take a more abstract setting, although from the point of view of descriptive set theory, it doesn't change anything important. So now I'm fixing a Polish space, so a separable and completely metrizable topological space. But everything what we do in that setting translates into, let's say, x equal to the real line, and whatever we prove for the real line, we also have automatically for an unaccountable Polish space, for example, a separable Banach space. But let us define a hierarchy of sets of this kind. So let us say that a set is analytic if it is a continuous image of a Borel set, and let us say that it is sigma 1, 1. Let us call the complement of an analytic set co-analytic, but now you know how to play this game. So inductively we define, let's say, a set to be pi 1n if it is a complement of a set that is sigma 1n, and how we do it what we do in the next step. Well, we take we take a product of our Polish space with some Polish space. If you don't like this quantification over all Polish spaces, you can, let's say, as I said, take a product with the real line, and this will give you exactly the same class of sets. So you can substitute R for Y here, and you take a pi 1 set and you project it down. Yes, so these are projections of pi 1 sets that live in the product of X and some Polish space. Okay, that's a nice hierarchy, and now the question is where is there a limit? Well, where is the limit of measurability, if there is any? Yes, so analytic sets are measurable. Co-analytic sets are measurable because they are complements of measurable sets. No problem. But is there an n where this changes? Where this changes, and maybe there is no measurability. Okay, let me leave it for a second, because I'd like to give you another look at this this business. So projective sets. So let us say that set is projective. If it is, let's say, sigma 1n, and this is the same as saying that it is sigma, or it is pi 1m for some m. Yes. Well, let us call them projective sets. And I would like to convey this message that we should think of projective sets as sets that are nicely definable with formulae that involve only quantifiers over Polish spaces. And now I would like to formalize this idea. Okay, so let us say that we have a formula, and now I'm maybe not overly detailed. So maybe I'm brushing something under the carpet because I would like to talk about formulae in the language of arithmetics. So, well, when we work in some Polish space, there is no way of explaining what do I mean by arithmetics. But if I work, let's say, in the space of the countable product of integers, so in the space of all integer sequences, then I have addition, I have, let's say, multiplication, yes, so I can define a basic arithmetic operations. And this is what I mean. And there is this equivalent, this Borel equivalence of uncountable Polish spaces, so that I can always translate, let's say, from some Polish space into the space of integer sequences, and then talk about arithmetics. But this will be not really that important for us, because the formulae we will be working with will have an almost clear translation into that framework. So let us think of formulae as for in that setting as formulae that where we have possibly quantifiers over some fixed Polish space. Yes, so we have a sequence of alternating quantifiers, exists for all, exists for all, exists for all, and we have at the end kind of an atomic formula that maybe involves parameters, so some fixed elements from the space, and that's it. So that's pretty much everything. So formula of this kind. Oh, and also this formula may involve quantifiers, but over a countable set. Yes, so we group the quantifiers, let's say, into quantifiers over Polish space and over something countable. And if you have a quantifier that is, let's say, in between of these alternating quantifiers over a Polish space, then and a quantifier over a countable set, then you can take a product, you can change the Polish space to the product space, and you can forget about, let's say, quantifiers over countable sets for that construction. So think of phi as a formula that is simple, and if it involves quantifiers, then they are over, let's say, integers. Okay, so in that case, we can say that the formula is projective when it is of this. So let us say it is sigma 1n. Okay, and this is one of the basic facts from descriptive set theory. You'll find it in Kekri's book that a set in a Polish space is sigma 1n if and only if it is a set where some formula of the form sigma 1n is satisfied. Yes, so this is a set that could be described by a formula by a sigma 1n formula of this way. So A is the set of all points in your space such that this formula holds, and you have a similar correspondence for the pi 1n sets and formulae. Okay, so we can think interchangeably about projective sets and projective formulae. And so we see that it is a matter, so it is related to definability. So to definability, where the main problem is quantification over possibly Polish spaces. So when we quantify about over a Polish space, yes. So for example, you have a Banach space and you separable Banach space, and you quantify over, let's say, all elements of the unit ball, then in most cases you lose Borel mass, but you retain projectivity of such a formula. So that's nice because we believe that such a sense should not be too complicated. Okay, so when we talk about definability, well, there is another approach to definability from the real numbers. So we can have a construction analogous to the construction of von Neumann hierarchy of all sets, but this time we will be, instead of taking the power set, we will be just taking sets that are suitably definable. So this time we don't start from the empty set, we start from the reals. And at the successor stage, well, what we do, we take all sets from the previous level together with all subsets that are definable by or from first order formulae, possibly with parameters from those sets. Yes. So, well, using real numbers, you can define, I don't know, complex numbers. Yes, you can define. You can keep doing. You can define, I don't know, the space is zero, whatever. So that's the idea. And at the limit stages, you take the union. And well, we take, let's say, the union of all such stages to define this constructible universe. So this is the smallest class model that contains the real numbers and all ordinals. So in that case, this is a model. I mean, model in the sense of inner model theory. So this is a class in which all the axioms of ZF are satisfied, but the axiom of choice fails in LFR, in the constructible universe. Okay, but in LFR, well, life is good. Life is good because we have all sort of wonderful results that are otherwise unavailable in ZFC because of the pathologies that come with the axiom of choice. Here we don't have the axiom of choice. So for example, all subsets of R that is constructible, yes, so that is constructible has the Baire property. Every subset is Lebesgue measurable. Because simply those, if you look at from the perspective of V, of the von Neumann universe, those pathological sets, they're not constructible, yes? They usually come from the application of the axiom of choice, but everything else that is in LFR has nice, let's say, topological and measure theoretic properties. But for us, importantly, every projective set is constructible. So in particular, in that setting, well, you have them in, well, they are Lebesgue measurable. They have the Baire property, but there is a cost of this. This is not a theorem of ZFC. You need to assume a stronger meta theory that will tell you that ZF is consistent enough for this to be to hold. So what do I mean by this? Here we assume the existence of a certain super large cardinal, and in that cardinal, if you remember this picture of the cumulative, if it exists, well then this hierarchy below it is a set model of ZFC. So not only it is a set model of ZFC, but actually there is a way of measuring consistency of ZFC should it be consistent. Yes, we can't prove it in ZFC alone by Goddale, but you can coin various notions of large cardinals. There is a hierarchy of large cardinals that tell you that if you assume that if you, let's say, assume the existence of such a cardinal, then this translates into consistency strengths of ZFC. So here, this theorem by Schellach and Woodin says that if you express a belief in consistency of ZF in some particular form, then well, you will be rewarded, and in that setting, constructible projective sets will be constructible, hence measurable, hence will have the property. Okay, so this is the black box. This is the magic I'm going to use, and with that, actually, the example of a result I'm going to present will be quite easy. So this is the hardest part to parse. And let me explain the difference of assuming large cardinals than, let's say, assuming the continuum hypothesis, because very often when we want to construct some pathological counterexample to something, could be, I don't know, an analysis in algebra, whatever, to show limitation of let's say some reasoning, well, we assume the CH, and okay, we have the construction. Usually there is some inductive construction, and we say, oh, we have a counterexample under CH. Very often you can actually negate the CH, assume Martin's axiom, and prove a similar result. Not always, but this is often the case. So you have like limitations almost from both sides. But this is not a phenomenon of this kind, because the continuum hypotheses, Martin's axiom, which is a very strong form of the Baire category theorem, and other axioms that are of this form. Maybe you have not encountered them if you don't work with non-separable business. But usually we use them, let's say, in the non-separable setting or uncountable setting to show that some pathology is possible. They come from the so-called technique of forcing that was invented by Paul Cohen to show, let's say, the independence of the continuum hypotheses. But large cardinals are, they don't see that, in the sense that for most of the forcing constructions of this kind, they don't see that. So when you assume some large cardinal hypotheses, then in that meta theory, you can still do your favorite forcing and have CH. You can still, let's say, have the negation of CH if you need it. So the flavor of the large cardinals is different. So it is not some ad hoc extension of ZFC. This is constructed, let's say, by forcing, and if you don't know forcing, then think of forcing as a kind of Baire category argument to produce some object, and that object lives in some extension of set theory. This is really an assumption of meta theoretic kind, because okay, we assume that there exists some cardinals with some particular properties, but this tells us something about the consistency of ZFC alone, whereas please, yes.
Sorry, there are some questions in the chat for you. Maybe you can take a look at
it. Yes. I'm not sure if I see them. More chat, yeah. In every model of ZFC that has a super compact cardinal, yes. Once you have a super compact cardinal, then all sets, then all, yes, that all subsets in R that are constructible are measurable, yes. Or consistency of ZF plus there is a no. You have them already. So that's the first. Possibility. Okay. And now, once you have this, well, you can get some implications about, let's say, linear operators from separable Banach from Banach spaces, from Frechet spaces. So in that case, when you have a linear operator defined or linear map defined on a let's say complete or on a Frechet space or Banach space, then it is automatically continuous. Well, this is this old argument by Banach and Pettis, yes, that if you have a bare measurable homomorphism from a Polish group, then it is automatically continuous. And actually, similar observation was made by Maitland-Wright. Yeah, okay, so this was about the Baire property, and Garnier used Lebesgue measurability. But in essence, that they proved that if let's say in a model where every set of reals in that model is either has the Baire property or is measurable, then all linear maps are continuous on a defined, let's say, on a complete space. Okay, and this will actually we will use it in some form. Okay, so let us say that the formula of set theory is delta naught if it does not involve unbounded quantifiers. Yes, so when you quantify over a set. So it is not like saying for every Banach space something happens, for every group something happens. Yes, because there are class many groups, Banach spaces, and so on. But if you can bound it to some particular set, I mean the range of your quantifiers, let us say that such a formula is delta naught. And now they are nice because they are absolute across all class models of ZF. So in particular, V, the class of all sets, proves your formula if and only if the constructible. You can prove it in the constructible universe. And here it is an interesting reduction. There is a weaker form of choice, the so-called the dependent choice, or the axiom of dependent choices. It states that that all binary relations with no countably infinite descending chains are well-founded, whatever. But it is actually quite intuitive when you look at maybe the most popular form. But a priori does not look like a delta naught statement. But there is a way of reducing it to such a statement. So if you want to work with the theory set F plus dependent choice, which means that you want to work, let's say, in V, and you assume it in V, therefore you assume it in V, so automatically it will hold in the constructible universe. After you prove it that it is equivalent to a delta naught formula. So there is some choice available in LFR, and you can think of DC as a form of choice that is sufficient to do functional analysis in separable setting. So if you work with separable Banach spaces, separable sister algebras, then you will have the Banach theorem for them, for example, using DC. Actually, Banach requires even something weaker. So all those pathologies that are associated to the Banach theorem, they arise when you apply it to monsters such as L infinity, but not to separable spaces. So separable spaces are good, and you can do your favorite form of functional analysis in the separable setting. And in that case, you rarely require something stronger than DC. So if you let's say replace AC with DC, pun not intended actually, then actually you don't get anything new. Okay, so what's the conclusion? The conclusion to this is that every pi1n or every sigma 1n formula, well, it is about Polish spaces. Yes, the quantifiers range over Polish spaces. So such formulae are, by the very definition, delta naught. Okay, so V and L of R agree on every such a formula. So projective formula are either true or false in the constructible universe. So the question, let's say, of measurability of projective sets cannot be tackled in the same way as I say, for example, the continuum hypothesis. So you cannot force, for example, these sets to be non-measurable, to some of them to be non-measurable, or to all of them to be measurable. This requires something different. And actually, what is it seems the right approach is to use the large cardinals. But there is one problem with large cardinals. So, well, I wanted to give you an example of one difference, conceptual difference between large cardinals and CH. But there is one more, yes, because we know that if Z of C is consistent, then so is Z of C plus CH and Z of C non-CH. But here, it may actually happen. So it is theoretically possible that ZFC proves that there are no large cardinals. It could be. It could be, even if it is consistent. And there was a guy from Belarus who was actually quite famous in PDEs, but he was kind of obsessed with those large cardinals. And every 5 years, he was announcing a paper that finally he found a proof that there are no large cardinals. Unfortunately, or fortunately maybe, every attempt was proved to be wrong. So there are some people who don't believe in large cardinals, but the current consensus, especially expressed by the views of Hugh Woodin, is that, well, we should not really disregard the large cardinals because they are tools that remove lots of maybe not pathology, but or maybe pathology, because sets that are constructible, such as projective sets, well, ought to be measurable. Okay, let me see how I'm doing time-wise. Okay. Okay, so let me let me move to the problem. So there was a problem. So now a change of topic to Banach space theory. But before I state the problem, let me introduce necessary terminology. So a filter on the integers is an upwards closed with respect to the inclusion family of sets that is also enclosed under joins, under intersections. Yes, so if you have something which is in the filter and something bigger, then this bigger set is also in the filter. And when you intersect two sets from a filter, then the intersection is also there. So only non-trivial filters are interesting, and non-trivial means those that contain the filter of cofinite sets, the so-called Frechet filter, because otherwise they are rather boring. Every filter, well, every family of sets, yes, you can identify with the family of indicator functions, and indicator functions live in the product space of 0, 1s. Here it is the product of countably many copies of 0 and 1s. What is it? It's the Cantor set. Yes. So it is the Cantor set, which is a very nice compact metric space. Therefore, you can assign all sorts of topological adjectives to your filter. So you can talk about Borel filters, projective filters, yes, meager filters. So whatever topological terms that comes to your mind, well, you can apply it to a subset of a Cantor set, in particular to filters. Every filter defines the notion of convergence. So, well, you have a sequence in a metric space, and it converges to X along the filter. Well, whenever the usual definition of convergence is satisfied, with the one exception is that now instead of taking a cofinite set, we take a set from the filter. So we think of those sets as big. So on a big set, we have that the distance from the entries of the sequence to the limit are, well, the distance is small. Okay, so when we are in a Banach space, well, we can modify the definition of the Schauder basis and say that, well, a sequence in a Banach space Xn is an F basis. Well, whenever the sequence of partial sums, so whenever for every element in your space, well, there exists a unique sequence of numbers. I call them A and X, so that the sequence of partial sums converges to X. So what is the limit of a sequence of partial sums? Well, that's the series. So here we think of series, but convergent in the sense of the filter. I suppose that it's quite natural. So we think of the limit along the filter. And now the question that was raised by Kadets, I think, in the early or late 80s, in a paper written in Russian still, was the following. So suppose you have an F basis in a space. So in particular, X is separable. And now, well, the numbers A and X, they are linear functionals. So that assignment is linear. So the question is whether they are continuous. And actually, the question was not asked in that generality, because Kadets was interested in this particular filter of statistical convergence, simply because you can translate statements concerning embeddability of little l1 to the space or to the dual space into things related to that filter. So this filter comes quite naturally in that setting. So he asked, what happens if you take this filter and the basis with respect to that filter? Are these functionals continuous? The problem is that's easy. The problem is equivalent to the continuity of the initial basis projections, as always, because they are just finite sums of simple tensors. And when you take the Fréchet filter, so you have that's a trivial remark. You have the definition of a Schauder basis, but for the Schauder basis, how do you prove the continuity of the basis projections? Well, actually, you use for example, you use the uniform boundedness principle, which gives you actually for free uniform boundedness. So not only are they continuous, but that there is a bound on their norm, which we use for the definition of the basis constant. So here, the problem is, well, okay, so there was one result, positive result in this direction, so that so there is a way of expressing filter generation. So I don't want to delve into that, but you can define what a filter basis is. And if this filter basis has cardinality, well, if it's countable, then actually you can use some sort of Baire category argument resembling the usual proof for the Schauder basis to prove that again there will be, the basis projections will be uniformly bounded. However, when you take the filter of statistical convergence, then already in the Hilbert space, you can find an example of a basis where the projections are continuous, but not uniformly. And this is not surprising because you can't generate this filter with fewer than continuum many sets. So, so this approach of mimicking, let's say, the Schauder basis case using uniform boundedness will not work here. Okay, and here comes a solution, mod large cardinals. When you assume that we have this strong meta theory, so we have super compact cardinal, then if your filter is projective as a subset of the Cantor set, then indeed the coordinate functionals are continuous. And the filter of statistical convergence not only is projective, but actually it is Borel, so it is as good as can be. Yes, it is Borel, and the solution is to use Pauli spaces, and by this I mean descriptive set theory and the constructible universe. Okay, so for this you need to have a suitable Pauli space that you will be working with. So if you have an F basis, then your space is separable. Therefore, it is natural to look at the space of separable Banach spaces. But what does it mean? And this is actually something that came to Banach space theory from von Neumann algebras, because Efros was studying let's say, the descriptive set theory of von Neumann algebra of factors, let's say, on a separable Hilbert space, and introduced a Polish space of von Neumann algebras simply by looking at the ball of BFH with the weak operator topology. And this idea came in particular to Banach space theory. But what Efros did was he did not really define a Polish space. Well, he did, but he didn't use it. He was only interested in the Borel structure. So he was interested in the Borel sigma algebra, not really in some particular choice of a Polish topology. And actually, now this is also used in C-star algebras, for example, by Elias Farah. There are papers from the 90s, Farah Kekries, where actually the Polish spaces that they use are different, and they depend on the context what they want to prove. But it turns out that the Borel structure is the same. And in those papers, they don't, in most cases, they don't pay too much attention to the Polish space. They only care about Borelness. So they work with the Borel with the Efros Borel sigma algebra generated by sets of this form. So we take a closed subset in our space. So here we take the universal space for separable Banach spaces, continuous functions on the Cantor set, and we define, let's say, sets E plus of U, where U is open, so that so closed sets that intersect some open set. So as I said, there is no canonical Polish space topology on the hyperspace of continuous functions on the Cantor set that would make the Efros Borel sigma algebra the Borel sigma algebra. But there are many such topologies, and there is a recent paper by Goddale and Saint-Raymond where they axiomatically define a topology that it would be good for that, and they say it is admissible. Maybe this term is overused, but let me stick with that. So if it is admissible, if those generators of the Efros Borel sigma algebra are open, and there is a subbase of the topology, so that every set in the subbase may be expressed as a countable union of differences of sets of the form E plus U, E plus V. And actually, there is a trick in descriptive set theory that because of the relation of belonging to a closed set is G delta in the appropriate set, you could modify slightly the topology to make this product Fx, where F is closed and X is in F, to be closed in the product of the hyperspace and the space. And this will be actually quite useful for us, because this is something that will be corresponding to the situation where you have a, let's say, a Banach space and a point from it, and you want to express this as in a single formula. And actually, what is important that when you take the subspace of linear subspaces, then this set is G delta, hence Polish. G delta subsets of Polish spaces are Polish. So that's nice because now we have, let's say, not only the Evros-Borel structure of separable Banach spaces, but now when you take a suitable topology, and there are lots of them, here I don't really need to fix them. If you are familiar, for example, with the so-called Wiesmann convergence, then this is an example. You take a closed set, you take a point, and you say that the sequence converges if the distances to the closed sets converge for every closed set. There are lots of topologies that are admissible in that sense. So we need to only pick one. And now I'm converging to the end. Is the following observation. So suppose you have a separable Banach space and a projective filter. So it is in some class pi 1n. And suppose you have a sequence, also fix that sequence. And consider the following formula that involves, let's say, sequences of scalars, yes, so elements of the product space of R to the n, and points in the Banach space. So the formula says this, that Z is the sum of the series with respect to the filter of AKZK. And actually, you can prove, this is not hard, maybe a little tedious, but not hard, that this formula has exactly the same complexity. So it is still pi 1n. So it means that, well, throwing in this this algebraic expression and passing to the limit does not really increase the complexity, which is not surprising because well, passing to the limits requires what? It requires an epsilon, but there are, let's say, countably many. You can take, let's say, rational epsilons. It requires taking a set from the filter. Okay, so this is the complexity of the filter. And that's it, yeah. So that's the moral reason why this has the same complexity. Well, the proofs require some computation, but not much. Okay, so we have this. Oops. So now let me maybe tell you how to put all the pieces together. So under the existence of let's say super compact cardinals, well, all linear maps that you can find in the constructible universe are automatically continuous. Very nice. Very nice because, well, everything is Borel measurable. Sorry, everything has the Burr property. And that's good. So if a Banach space is in the constructible universe, and actually this F basis is in the constructible universe, well, or you could prove in the constructible universe that this basis is an F basis. This is the correct way of saying this. Then automatically the coordinate functionals are continuous. Okay, so now if I take a projective filter, projective subset of the Cantor set, and I have the formula. So the formula, if a Banach space admits an F basis, then the coordinate functionals associated to that basis are continuous. That's the crux of the proof. So this formula is actually projective. So it's absolute across the constructible universe and V. So if it is true in L of R, then it is true in V. But we do know it is true in L of R by the cardinals. So, as I said, being true in L of R must be true in V. In V, we do have the axiom of choice. No problem, because here we haven't really invoked the axiom. Well, we didn't have to invoke the axiom of choice. It doesn't. So the moral of this is that, well, the axiom of choice well, it can't prohibit something from being an F basis. Maybe this is not the best statement. So what's the formula? How to formalize it? Well, you need to simply write it down. So let us try to parse it It looks horrible, but it works. So SB, so it is this Polish space of separable Banach spaces. So what we want to say, for every separable Banach space, and for every sequence in such a space, and here note that first what we did, we took a Banach space from SB, and then the second quantifier involves x, well, x to the power of n. So this is where this condition with closedness of this funny product set is actually convenient to use, because you can. So there is a way of actually turning every quantifier that you see here. We have 1, 2, 3, 4 quantifiers. I say 4 because there's an alternative. So it's an alternative of 2 times 4 quantifiers. Can be, let's say, expressed as a quantifier over some artificial Polish space, so that it is always the same Polish space, so that the definition of projectivity is satisfied. But these are standard, let's say, descriptive set theoretic tricks, and we don't have to worry about them. The only important bit is that that we can do this thing that we fix some object, which itself is a space, and then we can use it for quantification. And this follows from this requirement that this set of pairs fx is closed. That's the oh, sorry, that's the idea. So now what does it say? For every Banach space and for every sequence, either for every y, either it is not true that that it is an f basis. Yes, so it is not true that for every x there exists a unique sequence, blah blah blah, or it is, or well, it is an f basis and the functionals are bounded. Yes, so boundedness is now expressed in terms of the existence of a sequence of bounds, mk's, so that we have an m basis, and ak's are bounded. Well, the norm of ak is at most ak is at most mk. So that's the idea of the proof. Of course, there are some technicalities, but the technicalities, I would classify them as standard descriptive set theoretic tricks that you can learn from Kekry's book. So it turns out that we were we solved the problem, well, nearly solved, using, let's say, stronger meta theory involving Banach spaces by simply translating it suitably to the descriptive set theory, and then using the fact that it may happen that all projective sets are nice, in which case everything is solved kind of automatically. So I know it may look esoteric, I know it may look magical, but it works. It works under the assumption of large cardinals. So now you can ask me, is there a perspective of doing this without cardinals? And the answer is yes. So you can you can prove it if the complexity of the formulae of the formula is not big. So here, what is the complexity of this formula? Well, here we have 1, 2, 3, 4 quantifiers. So here it is negation. So I think that, okay, we have 4 quantifiers. So we will end up in the 4th level of the projective hierarchy. And these formulae, this formulae concerning, let's say, summation with respect to a filter, they don't contribute anything to the complexity. So what is in the 0th level, the Borel sets? So if you start with a Borel filter, then okay, this is nice. So then you have to count quantifiers, and there is a very deep absoluteness theorem by Schoenfeld and Levy, which essentially says, this is not 100% correct, but essentially it says that if instead of 4 quantifiers you had 2, then this would be absolute already without the cardinals. So this gives you a way of proving things that are problematic because of pathologies coming from the, I don't know, the axiom of choice or whatever. In a way, well, let's say by going through the constructible universe, and if the complexity of the formulae that you are working with is not too high, actually you can even avoid those black boxes. So here the Schoenfeld and the Schoenfeld-Levy theorem is the key. And I was working hard how to let's say reduce 4 quantifiers to 2. And the problem is that there is no suitable version of the principle of small perturbations for filter bases in that setting. I think if I had this, maybe I could prove it. But the problem is that the principle of small perturbation is saying that if you have a basic sequence and if you perturb it a little, then this perturbation will be also a basic sequence equivalent to the original one, involves going through the continuity of functionals that we don't have because we want to prove it. But if there is some substitute for this principle of small perturbations, maybe there is a way of proving this in ZFC alone without cardinals, but in the very same way. Okay, so I think I'm almost done. As I say, it was more like an advertisement because I have some further ideas how to apply this business in C-star algebras. I mean, not necessarily large cardinals, but this approach to Polish spaces of C-star algebras, let me say, not only the Borel spaces of C-star algebras. So definitely I'm going to have a follow-up to this paper, this time the realm of C-star algebras. I'll let you know if I prove something of interest. So thank you very much for your attention. I think that's all I wanted to say.
Thanks very much for your talk. Really liked it. Please let us know if you have that. We'll be happy to have you again speaking here. Do you have any questions for Kania? No questions then?
No questions then. Okay.
Okay, so I've never seen those things actually about those F bases. I thought it was very cool. By the way, just a very silly question, I guess, that a graduate student would ask. So what about the problems on like existence of those bases regarded as just Schauder bases? What is known about those things?
Well, okay, so this business started, I think, in the late 80s around Kadets. And his motivation for studying this was embeddability of L1 and related questions concerning, I don't know, the sequential fragments of the dual ball and so on. And I think that he was actually quite successful proving what we wanted to prove, so it kind of died out because it was used as a tool rather than an object of study. But this annoying question of automatic continuity remained, and I think Vladimir asked that 10 years ago during some conference, and Tomek Kochanek got interested in that, and this is how I learned about the problem. And I think they deserve more attention because I believe that they could be used to produce some further counterexamples, not only in Banach spaces, but maybe also in Banach algebras. That's a nice and quite natural topic, I would say. I don't know, maybe Bill has some other opinion. Okay, sorry.
Okay, well, thanks very much then. Evan.
Sorry.
Sorry?
I can't hear you, I'm afraid.
It's just a background noise. Okay, let me stop the recording then.